Welcome to the Explainer. Today, we're putting on our deep time detective hats and diving into the high-tech forensic investigation of how we actually know the definitive timeline of Earth's history. It's an absolutely fascinating journey, combining classic field observations with some seriously cutting-edge physics.
Think about it. This is kind of the ultimate cold case, right? How exactly do geologists piece together the precise sequence of events that happened billions of years before humans even existed? When you're standing there looking at a rock face or a canyon wall, you are literally staring at an ancient archive. But it's an archive without page numbers or publication dates. So here's our game plan for today. We'll start with reading the rock record, move on to uncovering missing time, check out the atomic clocks, dive into isotopic forensics, and tie it all together with the master timescale. All right, let's jump right into section 1, reading the rock record. Heading out into the field to look at the spatial logic geologists use, which is called relative dating, is just like analyzing a physical crime scene. We use these core principles first introduced by Nicholas Steno way back in the 17th century. And honestly, it's just logical, right? If a footprint is layered over a tire track, well, the footprint has to be younger. In geology, step 1 is the principle of superposition. In an undisturbed sequence, the layer on the very bottom is the oldest. Step 2 is original horizontality, meaning those sediment layers are originally laid down perfectly flat. Step 3 is lateral continuity. That just means these layers spread out continuously in all directions until they eventually hit a barrier or thin out. And step 4, cross-cutting relationships, tells us that if a feature, like a fault or maybe a magma dike, is cutting through a rock, the cutter absolutely must be younger than the rock it's cutting across.
And that actually brings us to this brilliantly simple relative dating concept, the principle of inclusions. It's so elegant when you really think about it. For a rock to contain a fragment in inclusion of another rock, that fragment had to actually exist first, right? It had to be there to get broken off and trapped inside the newer forming host rock.
Moving right along to section 2, uncovering missing time.
Now, as great as those principles are, the rock record isn't some perfect, continuous sequence. Sometimes the evidence has been eroded away or just completely destroyed, creating what we call an unconformity. You can think of an unconformity as a massive history book where somebody literally ripped out entire chapters. Because sea levels are constantly rising and falling and land gets uplifted and eroded, there are these long periods where no sediment is deposited at all or where existing rock is just scraped right off. And that leaves a massive blank spot in our planetary timeline. So to diagnose these missing chapters, we're on the lookout for 3 specific types of unconformities. First up is a disconformity. This is a break hidden right between parallel sedimentary layers, and honestly, they can be super hard to spot. Second is a nonconformity, which is where you have sedimentary rock sitting directly on top of much older crystalline, igneous, or metamorphic basement rock. And third is the angular unconformity. That's where you see flat sedimentary strata resting directly on top of older layers that were previously tilted and deformed by tectonic forces. Which brings us to section 3, the atomic clocks. Okay, so we've got our relative sequence from the field, but now we need the absolute dates. To assign a hard numerical age to the Earth, like its stunning 4.54 billion year age, famously figured out by scientist Claire Patterson using meteorites, we have to zoom way, way down into the invisible subatomic world of radioactive decay. The absolute heartbeat of the subatomic clock is a concept called half-life. Inside a rock sample, you have billions of unstable radioactive atoms, and we call those parent isotopes. Over time, these spontaneously decay into stable daughter isotopes. Now, while you definitely can't predict when one single isolated atom is going to decay, the decay rate for a massive group of them is completely 100% predictable. That specific amount of time it takes for exactly half of the parent atoms to decay, that's its half-life, and it acts as our ultimate geological stopwatch. Looking at the mechanics, there are basically 3 precise ways these parent atoms transform into daughter atoms. They can undergo alpha decay, which is ejecting heavy alpha particles made up of 2 protons and 2 neutrons. Or they might use beta decay, shooting off an electron when a neutron splits into a proton. Or third, they can undergo electron capture, where they grab an electron to neutralize a proton into a neutron. But hey, no matter which method it uses, the result is always a measurable physical transformation locked right inside the mineral crystal. Let's move into section 4, isotopic forensics. Let's crack open our isotope arsenal here. You'll see that different isotopes are basically built for completely different investigative jobs, all based on their half-lives. Uranium-238 has this massive half-life of 4.5 billion years, so it's absolutely perfect for dating the oldest rocks and the origins of the solar system itself. Potassium-40 is sitting at a 1.25 billion year half-life. But then look at carbon-14. Its half-life is only 5,730 years. That makes it our ultimate go-to for tracing very recent history. You can really see the stark contrast in how we apply these. U-238 gives us the deep time crystallization dates of igneous rocks, particularly by looking at those incredibly durable little zircon crystals. C14, on the other hand, well, that relies on atmospheric cosmic ray interactions that get incorporated into living things. So we use it to date once living organics, stuff like wood or bone. But it's only really useful up to about 57,000 years ago. After that, it basically just runs out of readable half-lives. And finally, we arrive at Section 5. The master timescale. This is where all the puzzle pieces finally snap together. We synthesize our spatial field observations with our laboratory physics. But even before mass spectrometers existed to measure those isotopes, scientists were already onto something huge, the principle of fossil succession. Because evolution produces this highly unique, ordered sequence of flora and fauna, scientists used what we call index fossils. These were widespread organisms that lived for a very short, very specific period of time, and they used them to globally correlate rock layers. Basically, if you find the exact same index fossil in a rock in North America and a rock in Europe, you know for a fact those rocks were laid down at the exact same time. So by calibrating those relative fossil sequences with our absolute atomic clocks, boom, scientists built this master timeline. It structures Earth's vast 4.54 billion year history into eons, eras, and periods. Just notice how the Phanerozoic eon, which is the time of visible life, only kicked off about 541 million years ago with the Paleozoic era. That was followed by the age of dinosaurs in the Mesozoic, and then the age of mammals in the Cenozoic. As we wrap up this explainer, I want to leave you with something to really chew on. Many geologists are now suggesting we've entered a brand new period called the Anthropocene, simply due to humanity's immense, undeniable influence on the globe. So think about it. When future deep time detectives are scanning the rock record millions of years from now, looking at the superposition of layers and testing the isotopes, what exactly are they going to find trapped in the strata of our current age? It definitely puts our brief little moment in geologic time into perspective, doesn't it?